Continuing our example here of finding the derivative function, part C, we've got g of x equals 1 minus x over 1 plus x. Okay, so these fractions always give us a good time with the difference quotient, so let's break this down. If we begin maybe just by looking at g of x plus h, then we'll have 1 minus the quantity x plus h over 1 plus the quantity x plus h, which, written simpler, is 1 minus x minus h all over 1 plus x plus h. Okay, let's put all that in to the definition of the derivative right there. And I've got this arrow pointing for a reason, but let's focus on everything else. So we've got g prime x equals the limit as h approaches 0, always the limit as h approaches 0. That's just part of the formula. And there we've got that g of x plus h minus the original g of x all over h, and that is a beast. Okay, so what we'll do, I'm just going to focus on that numerator because there is a lot happening there. I'm going to clean this up. Of course, we'll need a common denominator and that sort of thing. We've been in this situation before, but man, this is fraught for potential intimidation. So focusing just here, this is almost like work I'm doing on the side for a moment. Okay. Let's see, a common denominator. Well, as far as factors go, these denominators do not have anything in common, right? So because we're adding, we have to think of this as one object and this as a second object. So what we'll do, the common denominator will simply be the product between the two of them. So I'm going to take 1 plus x and multiply it top and bottom here. 1 plus x plus h, multiply that top and bottom here, and then put them all together. So because we've seen this situation before in other difference quotient problems, I'm just going to go ahead to this line, and hopefully you can follow me here. So I've taken the 1 plus x and multiplied it there. Subtract 1 minus x and multiplied it by this one. And then it's all going to be over the common denominator. Okay. From here, there's no easy way about it. We just got to multiply out this entire numerator and then combine like terms. And we're going to hope that it simplifies well for us like difference quotients usually do. There's only one way to find out. Multiplying these together, I'll just show you the whole thing. I'll let you think through the distribution, but I got this whole thing right there. Then I'm going to play it safe and just say subtract. I don't want to do too much at once. And then I'm going to put parentheses here and just multiply those together. So 1 times 1, 1 times x, and then I'm just going to leave that minus sign. That's too much for me to think through in one step personally. So maybe take a moment, maybe pause the video, work through that. And then, well, the simplification is very nice, right? We have 1 minus 1. X's just cancel out right there. Then we've got negative x squared minus negative x squared. Let's see here, negative h minus h, so that becomes negative 2h. But then negative xh minus negative xh, those are gone. Even these x's over here are gone. The only thing that survives in that numerator is minus 2h. And of course, we got our denominator still. So I will take that simplified version, put it back. I'm like picking it up where I left off. I'll put that back as the numerator. and that's all over h. So g prime x equals the limit as h approaches 0, my simplified numerator, all over this other h. Okay, now what we're going to do from here, think of this h on bottom as h over 1. And then I'm going to flip and multiply times 1 over h. Okay. And this is the crucial step where h's cancel. And at this point, I can successfully plug in my 0 for the 1 remaining h. Let me go to the next page. Oh, it looks like I showed a few more steps. Okay, so that's where the h is canceled. Then I'll plug the 0 in. Notice that as soon as you plug in the 0, we no longer write the limit in the front, because that step right there was the performing of the limit. When we're able to plug that in, now we have done the limit. We no longer write limit as h approaches 0. It's just a matter of cleaning this up. Once the 0 goes in, hey, check out the denominator. 1 plus x times 1 plus x. Let's just write that as g prime x equals negative 2 over 1 plus x squared. Okay. Now, in the same theme as the other problems, I'd like to just kind of reflect on this one, think about domain, that sort of thing. If you think about g prime, what x value is not allowed in g prime? You think, well, negative 1, right? What is g prime negative 1? You think, well, I can't do that. That doesn't exist. Exactly. Why is it that g prime would not exist at negative 1? Well, obviously we divide by 0, but even think back to the original function. Why is this? Maybe we could have actually known this from the beginning. Think back to the original g of x. It was 1 minus x over 1 plus x. What's going on at negative 1? Well, I have it written there already, but we know, even without that, at negative 1, what we'd have 2 divided by 0. That's a vertical asymptote. And I meant to write at negative 1. Well, if the original function has a vertical asymptote, then there's not going to be a tangent line there, and that tangent line is not going to have a slope if it doesn't exist. So it makes all the sense in the world that the derivative doesn't exist where there was a vertical asymptote at the original, because this is describing the slope of a tangent line. There's no tangent line. Okay. But everywhere else, it does. The derivative does work anywhere, any other value of x, and so does the original function. So we can get slopes of tangent lines at any other location. All right, that leads into a discussion. F prime of x not differentiable at a. So we're going to define this as you see. When we use the word differentiable, that means that you can take the derivative there. You would think that we would use the word derivable, that f of x is not derivable at a. You can't take the derivative, right? Some people do use that language, but that's not the official accepted vocabulary on this topic. The word that we use formally is differentiable, although sometimes slang you hear derivable. Okay, so for f of x to not be differentiable at a means that f prime a does not exist, and that was the case back with g prime negative 1, right? Actually, I see an error here. My mistake. This should just be f of x, not f prime. My bad there. F of x is not differentiable. means the derivative of f of x does not exist there. Okay. So let's kind of think about different ways that can happen. And we just saw one. When might f of x not be differentiable at a? So option number one, or case number one, if f of x has a vertical asymptote or a jump at a. So certainly if there's a vertical asymptote, you can't draw a tangent line. But even if there's a jump, right, and maybe just a quick sketch, so maybe, your function is doing this, and then it jumps down here. I don't know, right? That's f of x right there. You would think, well, at the moment, and this is a. Let's say that's a. At the moment that jump occurs, you can't draw a tangent line. You could think about a tangent line on the left. Maybe the way I've drawn it, it's kind of like going up. You could think about a tangent line here on the right. Maybe it's kind of doing that. But that's a different line. Even if the slopes were the same, it's still a different tangent line. So in order for the derivative to exist, there has to be one definitive tangent line. It's very much like a limit, a two-sided limit. Here, the two-sided limit would not exist at a. Well, neither does the derivative, because it makes sense. The derivative is based on a two-sided limit, right, as h approaches 0. Okay, so here, at a vertical asymptote or a jump, the derivative does not exist. But there are other cases that are not so obvious. All right, case number 2. There's a cusp, what we call a cusp at a. And let me show you a picture of what that is. Here is a cusp. Okay, so this is f of x. What a cusp is, it's like a sharp edge, or sometimes you even hear people say a corner. This would only occur if f of x is piecewise. Sometimes you get those, sharp edges on a piecewise function where, this is one piece, this is another, and they happen to line up. Okay, so you think, why would the derivative not exist at a cusp? Well, it's a similar argument to the jump. So think about, the tangent line coming from the left. So this tangent line is going up, like that. But if you think of the tangent line coming back this way, maybe it's kind of like doing that. And although they pass through the same point, these are very different lines with different slopes. And we need one definitive line to say that the derivative exists, will exist there. So here, the derivative at that one moment, just at that one point, does not exist because there's not a clearly defined tangent line with its slope. Okay. There's one more situation. This one is even less obvious than the cusp. What if there is a vertical tangent line at A? What would that look like? The tangent line goes vertical. Let me show you. Think about a graph like this. Okay, so it's coming in and it's increasing faster and faster. And just at that moment, just for a split second, the tangent line, here the tangent line is getting very steep, very steep. And as we get closer, and just for a moment, that tangent line actually goes completely vertical. And then just after that, it starts to level off again. Why would the derivative not exist here? Well, what's the slope of a vertical line? Well, we say it's undefined, right? The slope of a vertical line is undefined. So, since the derivative describes the slope of the tangent line, here the tangent line does exist. It does have, you could even say it's got an equation, right? X equals A is that vertical line. but there's no slope to it, and so the derivative there will not exist either. Just to give you an example, you think, like, when would this ever happen? There's actually a function that's fairly common to us where this happens, where this sort of shape occurs. Cube root of x would be 1. F of x equals the cube root of x has a vertical tangent line at a equals 0. I invite you go into Desmos and graph the cube root of x and just take a look at it, right as it passes through the origin. It has this very shape here, except where that point is right there at the origin. And we will actually see when we start chapter 3, we'll be able to get f prime x for the cube root of x. It's pretty difficult to do algebraically. It's not totally outside of our realm, but it would definitely take some time and some discussion. That's really not entirely necessary, unless individuals want to chat about it. That'd be fun. But as far as the teaching goes, it's really, yeah. Okay, we'll leave off the discussion on how to get f prime x out of cube root x from the definition of the derivative. But we could do it. And if we were to see what that derivative function is, we'd be like, oh, yeah, I see why there's a vertical tangent line there. And then, yep, that matches with the graph. Okay, anyway, go check it out on Desmos just visually. We're going to stop this video here. We got part 3 coming up.